Last section we talked about the line integral of a vector field over a curve. And in the first section of this chapter, we mentioned that we can get a vector field from any scalar function of 2 or 3 variables by taking its gradient. So we want to see how these two concepts can be paired together. And it turns out it works out very well. So let's take a curve, some curve C that's given by some vector value function r of t. T here is going to go from A to B. We're going to take some scalar function, f. This could be f of xy or f of xyz. I'm going to write this in 3 dimensions, though everything will actually work out the same in 2 dimensions. The gradient of f, recall, is just going to be the derivative of f with respect to x times I, plus the derivative of f with respect to y times j, plus the derivative of f with respect to z times k. I'm also going to go ahead and write r. I'm going to write r in terms of its components. I'm just going to call those components x, y, and z. But remember, these are all functions of t. When we've done that, the derivative of r is just simply the derivative of x with respect to t, which I'll just write dx dt, then dy dt, and finally dz dt. These are the vectors that we're going to be using in our line integral. So we're taking the line integral over this curve of the gradient of f dot r dr. T is going from A to B. This turns into a dot product of the gradient of f at r of t with the derivative r, and then dt at the end. So we're taking the dot product of these two things. So what this really means is that each of these is being evaluated at t, but we don't really have to write, I'm not going to write of r of t in for each of those. But remember how we take the dot product. We're just going to multiply the corresponding components. So we're multiply df dx with dx dt. And then we add that to the other two. And at this point, we want to stop and recognize that what's inside the integral right now is something we've seen before. If we think back to chapter 14, recall that when we composed a function of 3 variables with a function of a vector value function that gives us that starts with a that takes in 1 variable and outputs 3 variables, that composition we can actually compute the derivative of by using the chain rule. This thing right here is just the derivative of f with respect to t. Or really, I should specify that it's the derivative of the composition of f with r of t. Or, yeah. So here, this is really just, once we compose f and r, this is now just a function of 1 variable. And so we can rewrite this whole thing as the integral of the derivative of this composition. I need one more. But once we've actually written this as an integral of a derivative, right now we are just working with the integral of a derivative of a function of 1 variable because we have this composition. We can use the regular fundamental theorem of calculus just make this the function f of r of t evaluated from a to b. Or in other words, we have f of r of b minus f of r of a. This result, because it's so similar to our fundamental theorem of calculus, we're going to refer to as the fundamental theorem of line integrals. Basically, if we have any smooth curve and we have a differentiable function of 2 or 3 variables, then we can integrate its gradient by just evaluating that function at the endpoints of our curve. So this is, like I said, this is very similar to our fundamental theorem of calculus, where if we took the integral of a derivative of a function of x, then we can just take the function whose derivative is the integrand, evaluate it at the endpoints, and subtract. It's just in our fundamental theorem of line integrals, the derivative is the thing that's playing the role of the derivative is the gradient, and instead of just a normal integral, we have a line integral. But otherwise, it's exactly the same kind of thing. But the consequences of this theorem might be more wide-reaching than you might think. This means that if we have any conservative vector field, one that is the gradient of some potential function, we can take line integrals over any curve by just looking at the endpoints of that curve. So if I were to say take a point here, say point A and point B, and I want to get there by some curve C1 versus getting there by some other curve C2, the result is going to be the same thing. If f is conservative, then the integral over C1 of f equals the integral over C2 of f. Because both of these are going to be equal the difference of the potential function at these 2 points. So I should say here that if capital F is the gradient of little f, then both of these are equal to little f at b minus little f at a. I should specify here that both these curves are going from a to b. The direction kind of matters a little bit. If we reverse the direction, we actually introduce a minus sign to our integral. You can kind of see that here, because that basically means I swap a and b. But that's even true even if it's not a conservative vector field. Another consequence of this is if I start at some point, and I don't want to pick C for this, let's call this D, and I have some curve that starts at D and ends at D, we call this a closed curve. Let's call this C3. The integral over C3 of capital F, as long as we are conservative, then this is going to equal the value of little f at D minus the value of little f again at D. So we're always going to get 0 here. So over any closed curve, a conservative vector field has a line integral of 0. We're going to call all this path independence, or we say that the integrals of f are independent of path. And we're going to be investigating the consequences of being path independent, and we're also even going to show that path independence itself directly has some consequences. One thing that may not be clear right away, though, is that we only really need to look at closed curves to actually specify that these are path independent. Because if I were to look at the integral, look at these two integrals over C1 and C2, if I only know that the integral over any closed curve is 0, then I could take the curve where I start at A, follow C2, and then follow backwards along C1. That whole integral is the integral over c2 minus, because we're going the wrong way around c1, it's minus the integral over c1. And since that's a closed curve, I would need that to equal 0. But all that means is that now I've got this difference equals 0, so these two integrals have to be the same. So this is actually all that we really need to make sure this all works. Though we don't really need to actually use that a lot for what we're going to be doing with this. But it is kind of important that we don't really need to have the full weight of path independence. We just need this smaller condition to get the entire thing. So we've noticed here that being conservative implies path independence, but it turns out we can kind of go the other way. A vector field that we don't know anything about it being conservative right off the bat, but we can say that its line integrals in its domain are independent of path. That is enough to say that we have a conservative vector field. We do have a few conditions on our region, though. We're going to say that our region has to be open. That just means that it doesn't contain any points on its boundary, though that will have a consequence that we're going to use. But specifically here, and I wish they would have put this all in one line, but they also specify that it needs to be connected. A connected domain means that any 2 points can be connected by a path. A path meaning a curve from a point to another point. So if we're saying our region D, actually I should probably make the boundary of it dashed, because it doesn't contain this boundary. This is an open region. But if I take any point in here and any other point in here, there is some path that stays in D that goes from that point to the other point. There's not two separate pieces to this where I cannot jump from one to the other. So if I were to draw something like this, I have a point over here and a point over here, and there's no way I can get from one to the other. This just doesn't work. And in fact, this fact about being able to connect 2 points by a path is actually going to play a big role right away. Because what I'm going to do in order to find a function little f that is a potential function for capital F is I'm first going to pick some base point. I'm going to call it AB. So this is a point AB over here. If I take any other point, let's say xy, because I'm able to take a path from AB to xy, I can actually find an integral, let's call this C, some integral along C of capital F dot dr, and this integral won't depend on which path I actually take. So I can pick any path as long as it stays in D, so this integral even is defined. I can take any path and I always get the same result. In fact, the book actually likes to write this as the integral from AB to xy. Just to specify that it doesn't really matter how we get from AB to xy, we get the same result either way. And since we get the same result either way, we're just going to call that result f of xy. And I'm going to claim here that this little f that we're defining is in fact a potential function for capital F. Now, it's not necessarily the only potential function possible. Obviously, if you add a constant to f before you take the derivatives to make the gradient, it's not going to change the result. So adding a constant to little f is going to give you a brand new potential function. But what that actually really means is that we picked a different base point. This choice of base point was very arbitrary in the first place. If we pick a different base point, then we get a different result, technically, but the result actually turns out to just be a scale, a constant added to our function. So we want to show this little f is a potential function for capital F. That means not only do we need to show that f has partial derivatives, but we also want to show that capital F is the x derivative of f with respect to x, and then the derivative of f with respect to y times j. So the components of capital F have to be those partial derivatives. Now I'm going to label the components of f as p and q. So I'm wanting to show that p is the derivative of f with respect to x, and that q is the derivative of f with respect to y. Really, I'm just going to show one of these. I'm going to show that p is the derivative of f with respect to x, because doing q is exactly the same thing. It's just going to be a repeat of exactly what we already did for p. So I'm not going to bother showing it twice. So let's actually take our point xy and compute the x derivative of the function f at that point. Now remember, when we're taking the x derivative, we're allowing the x to vary and not the y. So we're going to be looking at points that are in the same horizontal line as the point xy. Now we're actually going to take advantage of the openness of our domain. The fact that D is open means that for any point that's in D, there is a disk around that point that is contained completely inside D. Specifically, what that means is that we're allowed to take derivatives by taking limits because we have enough free space around our point. That's really what all that's really coming down to. But we are going to specify here that we're going to find points in our disk, in this little disk, by adding an h to our x value. So we don't want to change y, we want to look at points on the same horizontal line, but we want to change that x value. And I'm specifying here that h is positive. Technically here we could also do h being negative. It's not going to really change anything. I'm only going to work one side of this, but you'll see that it'll work out pretty nicely. So here we're adding some h to it, so we get a point over here. We have we have x plus h comma y. Now what we're going to do is we're going to we want a path from AB to x plus h comma y. But to do that, we're actually just going to take a path that first stops at xy, and then from xy to x plus hy, we're just going to take this horizontal line. That horizontal line is always going to be inside that disk. It's always going to be inside the domain D. In fact, that's really the main reason why we want to take a disk in the first place. We want to make sure that these points are definitely inside D. So that means that the integral from AB to x plus hy, since our path actually has two pieces to it, we can take the integral over each piece separately and add the results together. So we have the integral from AB to xy plus the integral from xy to x plus hy, though we are looking at this particular curve of L. This first integral, that's what we've been calling f of x plus hy. So remember, the the little f just means the integral from AB to whatever our point is. So this is the integral from AB to our point, so we put that point into little f. This here, for the same reason, is just little f of xy, and then we still have our integral over here. I'm going to go ahead and rearrange this. I'm going to move the f of xy over to the other side. So that equals the integral that we have. But then I'm also going to go ahead and divide everything by h. And you might be able to see where I'm going with this. This form that we have right over here looks very much like what we do for derivatives. But to take the derivative, we are going to have to take the limit as h goes to 0. But before we even try to do anything with that, let us simplify this integral. And I'm going to do that specifically by giving the curve L. I know what that curve L is. I can go ahead and work out what it is. So here, L being the line from xy to x plus hy, I can go ahead and write that. Let me move this over a little bit. So we're going to give this by a vector value function r of t. The y values are always going to stay the same, so this is always going to have a yj in it. The x component is going to change. It's going to change from x to x plus h. I'm going to do that by just doing x plus t, where t is going to go from 0 to h. And in fact, the fact that I'm letting h be positive is kind of why I picked, well, the fact that I want it to go from 0 to h is why I picked h to be positive. If you want to do it another way, you could say h be negative and then go from h to 0, or you could kind of start the same way but do x minus h at this first part. It gets a little bit messy just having to deal with the two different cases separately, so that's why we're only looking at one side of this. Taking the derivative of r is pretty easy because x and y here are not dependent on t. Those are constants. We're not moving the point xy. The only thing that changes here is this t here. So the derivative of r is simply I. The derivative of t with respect to t is 1. And so this integral is going to be the integral from 0 to h of f of r of t, dotted with r prime of t. But remember, f is pi plus qj, so you can go ahead and write that in here. And then when we put in r of t just follows this formula here. So I'm just going to take p of x plus t, comma y, I, plus q, x plus t, comma y, j, and that's dotted with I. Because I is our r prime. But if we're taking the dot product here, we take, well, 1 times p plus 0 times q, so the q goes away. It's not involved here anymore. We're simply taking the integral of p of x plus t, y, dt. And that's what we're going to go ahead and replace in this formula. So now we have this particular quotient is equal to 1 over h times this integral. We're going to take the limit as h goes to 0. This side over here, of course, turns into the derivative of f with respect to x, technically at the point xy. Over here, well, now we're essentially turning this into its own derivative, where we essentially are taking the derivative with respect to x of the integral from 0 to x of p of ty dt. We've turned this integral into a derivative, but it's a derivative where the actual variable that we're differentiating with respect to is one of our limits. And recall from the original fundamental theorem of calculus, or at least one version of it, when we do that, when we differentiate an integral of this form, we simply get the integrand with our variable replacing the integration variable. Basically, this turns into p of xy. So the derivative of f with respect to x not only exists, but it is equal to p. Of course, we get the exact same thing for y, though we're not going to show it. Everything works out very similarly, except we take vertical lines instead of horizontal lines this time. So the y derivative of f is equal to q. In other words, the gradient of little f not only exists, but is equal to capital F. So this condition of being path independent guaranteed that we get a potential function for capital F. In fact, our path independence immediately results in giving us that function. By just looking at path integrals, we get our potential function. Of course, it's more likely to know that something is conservative rather than knowing that every single integral does have path independence. So it's more likely that we're going to go the other way with this, the way we started with. But this does lead to the unfortunate thing that we do need to find out when vector fields are conservative. It's even more important now that it has this additional idea of path independence behind it. So how are we going to actually figure that out? Well, one thing we can do is look at derivatives. If we start with some vector field, f equals pi plus qj, and we already know it's conservative, what does that mean about p and q? Well, that does mean that there is some little f, some potential function, where p is equal to the derivative f with respect to x, and q is equal to the derivative f with respect to y. If we look at the derivatives of p and q, what does that mean? Well, it means that we're looking at the second derivatives of little f. Well, if we differentiate p with respect to x and q with respect to y, then we're getting the not mixed partials. So those aren't really too helpful. The mixed partials are going to be a little bit more helpful to us. So we're going to look at the derivative of p with respect to y. So the variable that we didn't differentiate to get p. That means we get the second derivative of little f, first with respect to x to get p, and then with respect to y. If we do the same thing with q, but this time differentiate with respect to x, now we're looking at the second derivative of f, first with respect to y to get q, and then with respect to x. These look very similar, except the x and the y are switched. But if you remember from back in, I think it was chapter 14, we had what we call Claro's theorem. Which says that as long as these partial derivatives, these second partials, are continuous, which is not a very strict condition once we already know that they exist in the first place. As long as these are continuous, then Claro's theorem guarantees that these two things are equal. Or in other words, the derivative of p with respect to y has to equal the derivative of q with respect to x. If f is conservative and its component functions actually have continuous partial derivatives, then we always have to have the derivative of p with respect to y is equal to the derivative of q with respect to x. We can even go ahead and write that down as a theorem. And this is a pretty simple condition to check in a lot of cases, and it can immediately tell you when a vector field is not conservative. If a vector field, if we start with a vector field that we don't know whether it's conservative or not, we take the derivatives of p and q with respect to y and x respectively, and those do not give us the same result, then we automatically know that f is not conservative. There is no potential function. There cannot be a potential function. And unfortunately, the reverse is not actually true. Just because the derivatives equal each other does not necessarily mean that capital F is a conservative vector field. Now, it almost does. It's actually really close to implying the reverse. But we actually do need to make a restriction on our domain in order to make that work. So here we have our result, where we're basically saying that if we have a vector field where the derivative of p with respect to y and derivative of q with respect to x are equal to each other throughout the entire domain, then f is conservative. But they toss in an extra condition here called simply connected. What does simply connected mean? Well, simply connected, first of all, a simply connected region has to be connected. If we have any 2 points in that region, they have to be able to be connected by a curve. But simply connected is slightly more than that. Simply connected also requires that we don't have any holes in our graph, in our region. So let me draw some examples here of things that are simply connected and things that aren't. So, I mean, just a blob here, or you can even take a disk or something like that. Those are simply connected domains. For not simply connected, you can have something where it's in 2 pieces. That fails just simply because it's not connected in the first place. But we can also have something where it has a hole in the middle of it. So here, there's a region that's inside of our region that's not part of the region. The way we want to actually think about that is, can we take actually, let's put this in a different color. If I start at some point and I make a closed curve, so it comes back to that point, can I enclose some point that's not in our domain? If that is possible to do, then we're not simply connected. So we cannot enclose points that are not in by a curve, or let's say path in D. That's the thing that we need, that simply connected is actually excluding. We cannot have closed curves that go around points that are not in D. If that is possible to do, it is no longer simply connected, and so the reverse, this theorem is not necessarily true. We will take a look at an example of that happening in one of our example exercises. But for now, we've gone through all of our theorems about all this kind of stuff. We've gone over our fundamental theorem of line integrals. We've talked about path independence. In the next video, we're going to go through some exercises. For one, we're going to look at identifying when some vector fields are conservative. We'll show that they are conservative, and we'll even make use of that idea in order to evaluate line integrals easily by looking at potential functions. But that's all we have for this video, and I'll see you in the next one.